Alrighty, welcome everyone to the first seminar of the semester. I want to introduce our speaker today, Scott Niekum. So Scott did his PhD at the University of Massachusetts Amherst. He then did his postdoc at CMU. He's actually a local Pittsburgher. Grew up here and went to did his bachelor's, master's here as well.
Just bachelor's.
Just bachelor's. Oh, okay. Became active as a postdoc with Chris Atkinson, and now he's at the University of Austin, or University of Texas Austin. I can say that although he didn't write the book, he did write the review paper on learning from manipulation. And it's been an absolute pleasure working with him on that. I remember while we were writing it, there was one point where Scott wrote multiple pages on safety for robot learning. And unfortunately, we had to trim that back. But I'm very excited to see that he is going to be talking about this topic again today. And before I switch over, I just want to remind everyone that there is a post-seminar reception in Gathertown. You should have gotten an email, like in the email, the announcement with a link to that. So hopefully a lot of people can join there and also, continue the discussions at that point. All right, with that, I hand over to you, Scott.
Great, thanks so much, Oliver. Yeah, I'm excited to be here. It was supposed to happen in February, but I got the flu and then COVID hit and everything. So it's exciting to finally be here. So thanks so much for having me virtually. So as Ollie said, today I want to talk about safety. And when somebody says safety to me, I never have any idea what they're talking about because it means so many different things to so many different people. So I just want to start out with a definition of what I'm talking about today. So when I say safety for the rest of the day, what I really mean is correctness plus confidence. So correctness is just, to me, meeting or exceeding some measure of performance. This could be anything ranging from, making sure you don't violate some temporal logic constraints to, making sure you're above some level of return in a reinforcement learning problem, for example. And then we want to have confidence over this correctness metric. So a guarantee, usually probabilistic, that we are meeting our correctness metric. And so that's what I mean when I say safety. I think it's a pretty broad sort of umbrella term for most of what people mean when they say safety, but probably not all definitions. Okay, so why should we care about safety in robotics? There's been a lot of work that's been done in safety, both sort of in robot and non-robot contexts in recent years, largely in the off-policy evaluation and reinforcement learning communities. Two particular problems that have gotten a lot of interest are safe off-policy policy evaluation, or the OPE problem. And so this is where we want to determine a probabilistic lower bound on the expected performance of some policy that we usually call the evaluation policy, given data generated by some other policy that we call the behavior policy typically. And so, for example, if we have some walking soccer playing robots, for example, and we have a walking policy we're pretty happy with. It's not the fastest in the world, but it doesn't fall over and break itself. And we have another policy that we think might be a lot faster that we'd like to test. We don't actually want to run it on the robot because the robot might fall over and break itself. We'd like to be able to do an off-policy evaluation to see if we should switch policies or not by using data from the policy we trust. So a related problem is the safe policy improvement problem. So if you do any reinforcement learning research, you might be familiar with curves that kind of look like this, where you eventually asymptote to something pretty good or not, depending on your algorithm. But you have these big ups and downs along the way. And if this is an investment strategy, or if it's a robot that can fall over and break itself and cost you money, right? You really want to see monotonic improvement. You don't want to see these ups and downs. And so the way that safe policy improvement typically works is that there's sort of a proposal stage and then an evaluation stage using OPE usually to make sure that with high confidence you're monotonically improving. So these are sort of two areas where there's been a lot of progress. They're very difficult problems. They're very sample intensive usually. They're still very much open problems. And despite the progress that's been made, I think it's still not enough. Not just that not enough progress has been made on these problems, but that these aren't even sufficient questions to be asking to get robots into people's homes and workplaces. And so if we really want to get robots out in the world, there's so many different things we are going to want robots to do, so many different environments. We want end users to be able to program the robots, to specify new tasks that they want the robots to do, meaning we need imitation learning. And we need safe imitation learning, because right now, the state of the art in imitation learning is essentially, or maybe I should just say the common paradigm in imitation learning is take some data, demonstrations, throw it at your favorite imitation learning algorithm, close your eyes, cross your fingers, and hope it works, right? And nobody is going to want to use algorithms that operate that way. We cannot deploy this. But that's what everyone's sort of working on, and I think we need a new paradigm. And so what I want is a robot that knows what it knows. So I show the robot some demonstrations. It thinks for a while, comes back with a policy, and basically says either, with high confidence, I believe I'm almost as good as you, the expert at this task, or I'm not sure, I need more data. So what's this mean? I mean, this is a much harder problem than the safe policy improvement problem, right? And like policy evaluation, policy improvement, you know the reward function. The only uncertainty is about how well a particular policy operates with respect to that reward function. Here, we have that uncertainty, but we also don't know the reward function. All we have are the demonstrations. So there's a double uncertainty. So this is really hard, right? So we want to upper bound the policy loss, the difference in performance between the robot and the human demonstrator. We want to do this probabilistically with high confidence, and we want to do it without knowing the ground truth reward function, which requires, this kind of weak theory of mind, where you have to think about, well, given what I was shown, what are all the reward functions that could have been in the person's head, and can I bound this value difference, the value of the expert's policy minus the value of the robot's policy? We bound that within some epsilon with high confidence, like, probability 1 minus delta. So unsurprisingly, this is challenging, but this is what the talk's going to mostly be about today. We're going to start out with just a sort of theory of safe imitation learning and a baseline algorithm for doing it that is completely intractable. And I'm going to spend the rest of the talk fixing that and showing how we can start scaling up toward actually being able to do this kind of a thing on a robot. Especially in part 3, I'll be talking about a lot of our work on off-policy evaluation that I think is actually of interest to a much broader community of people than just people involved in like safe learning research or inverse reinforcement or imitation learning. Okay. So we're going to be building on some basic building block ingredients that a lot of you are probably familiar with, but I'm just going to give, sort of a quick overview to make sure we're all up to speed. So if we go back to the original 2004 Bielening inverse reinforcement learning paper, the idea is that, we're going to show the agent demonstrations, and we want it to infer the reward function that was essentially in the demonstrator's head that caused them to behave the way they behaved, usually so that we can run RL on top of that and learn a good policy and imitating policy. And the idea here is that we're going to assume that we have some features, phi, and that we can parameterize the reward function just by a set of weights. So the reward we get at any state is just going to be the weight vector W dot the features. And we can do that without loss of generality because the features can still be nonlinear with respect to the state. It's just that then we use a linear combination of those to get the reward. And so that means that we can write the value of a policy over some distribution of starting states just as this expectation of discounted rewards, right, that we're going to see when getting rollouts of policy pi. We can rewrite that as W dot phi, as we just said, and we can actually pull W out of this expectation so that the expected value of a policy is really just W dot the expected discounted feature expectation, the expected discounted features that you're going to see when rolling out policy pi. So I'm going to call those discounted feature expectations mu of pi, okay? And the goal of inverse reinforcement learning in this context is that we want to find a reward function whose optimal policy matches the expert's feature expectations. Why? Well, because if the expert's feature expectations are matched, then expected return is also identical. Because remember, the value of the policy is just W dot the feature expectations, right? So just match the feature expectations. So you can't always match the feature expectations exactly, though. And we are not the first people to try to think about bounding the performance of imitation or inverse reinforcement learning. And in fact, in these papers, both the Abil and Ng and this Said and Shapir paper, there's they have a bound where they basically say, without loss of generality, if we bound the one norm of the weight vector to be less than or equal to 1, then we get this really simple bound that you can bound the policy loss between the expert and the robot by the infinity norm of the difference between the feature counts of the expert and the feature counts of the robot. And the intuition behind this is that the reason we're using the infinity norm here is it's basically a worst case bound. We're saying, what if we spent our whole budget of 1 in the reward function or the W vector on the feature where there's the biggest difference between the human and the robot. So penalize that difference the most. And that's like the worst case scenario, right? But because it's a worst case bound, this ends up being really loose and like needing lots and lots of data. And in fact, you'll notice this bound actually requires us to know mu of pi star, the expert's feature counts perfectly, but we don't. We just have samples, which are the demonstrations, right? So these papers actually use sort of like a concentration equality or a Hufting style bound to say, well, if you want your policy loss to be guaranteed to be less than or equal to some epsilon with probability 1 minus delta, you need at least M demonstrations. But M tends to be huge. This is a bound, but it's sort of a vacuous bound in that it's like, even for simple grid world problems, you plug in the numbers and it's like tens of thousands of demonstrations or something. So this is not really a feasible route to go about doing safe imitation learning that has guarantees. So what do we do instead? Well, for the rest of this talk, I'm going to go through and I'm going to try to challenge some statistical assumptions that the inverse reinforcement learning, imitation learning communities, reinforcement learning communities have made that aren't very good and that we can improve. And the first assumption I want to tackle is that if we don't know the ground truth reward function, the worst case reasoning is the best we can do. And you know, even just a quick inspection shows that like worst case reasoning is fishy at best, right? If I show you a bunch of demonstrations where I avoid lava, and then I try to get some bounds and I say, oof, well, there is this adversarial reward function where the best thing you could do is jump in a pit of lava. That seems a little odd, right? Because if that's true, why did all the demonstrations avoid the lava? It just doesn't make sense. So we're just going to make the very simple point that it seems like it should be much more efficient to consider the likelihood of reward functions when we're assessing risk. Okay, so how do we do this? We're going to need a couple ingredients first of prior work. So the first is, again, something you may be familiar with, Bayesian inverse reinforcement learning. So far, the IRL methods we've looked at just give you a point estimate of the reward function. This gives you a full posterior distribution. We are going to use MCMC to just sample from the posterior of reward functions given the demonstrations that we have. And the real piece of interest here is the likelihood function, right? And so the likelihood, given some reward function, the likelihood of seeing particular demonstrations is going to take this Boltzmann rational or softmax form. For the reward function R, you're going to solve for Q star. And we're basically just saying we're exponentially more likely to see actions that look good under Q star than actions that look worse. That's it. That's the assumption we're making. And that you can kind of control with this temperature parameter C how optimal you think the demonstrator is. That kind of interpolates between perfectly optimal and perfectly random. This is not really how people operate in practice, but it actually turns out not to be a terrible assumption empirically in a lot of ways. And Anka Dragan actually has a really nice paper evaluating Boltzmann rationality. All right, we need a second piece that we're going to build on, which is a metric called value at risk that is often used in the finance community. There are other variants of this too, like conditional value at risk that we use in some of our work, but value at risk is the simplest one to understand, so that's what I'll present. So the idea behind value at risk is that it provides a bound on how bad things can get some percentage of the time. So let's say finance, there's some investing strategy I want to use, And the value at risk of that strategy says, based on historical data, no more than 5% of the time will I lose more than $500 when I'm using this strategy, for example. And so you can imagine that basically the way that you can write this out is by looking at, the inverse CDF of a distribution. You find this alpha cutoff. So if you're computing like the 95% value at risk, the alpha cutoff is going to be the dividing line between how bad is this point here between the 95% best losses and the 5% worst losses. And that's what's called like the alpha value at risk. So this gives you a metric of, instead of worst case, like 5% worst case, right? It's a little bit softer. And it allows you to adjust, how much appetite for risk you have. Now notice that if you compute this distribution via samples, we're not taking into consideration how many samples we've actually seen and how accurately we're representing this. So if you actually want to have confidence over your estimate of value at risk, you need to add a single-sided confidence bound as well. And then that finally allows you to make statements of the form that we want to be able to make for our work, which is something like, with probability 1 minus delta, no more than 1 minus alpha of the outcomes will be worse than epsilon or x. And then you just pick a sort of a delta and alpha like 95% each, solve for x and check if it's within your risk appetite or not. And so to translate this to the robot problem we're talking about in imitation learning, we want to give some demonstrations to a robot. We'll pick, again, a delta and an alpha. And what the robot's going to tell us after it computes a policy is basically, with high confidence, 99% confidence, no more than 5% of the time do I think I'm going to be more than epsilon worse than you who taught me. Or I need more data. I can't give you that kind of a guarantee, right? So this would now be a robot that knows what it knows. Now, what I haven't told you is what's the algorithm to actually do this, right? So let's put some of these ingredients together and make an algorithm that's completely intractable, but that does what we're saying. And then we'll go back and fix the tractability issues, okay? So here's how safe IRL works. We start with expert demonstrations and we run Bayesian IRL, okay? So that's going to give us this distribution over reward functions. So what we're going to do is we're going to pick a reward function. Let's say we go with the map. We could go with the mean. We could do a lot of other choices. But let's say for now, we go with the maximum a posteriori reward function. And what we're going to do is something that's already intractable. We're going to solve for the optimal policy for that. And in fact, Bayesian IRL requires you to solve for Q star a whole bunch of times. So it's already intractable. But we're going to solve for pi star. And we'll call this pi star map. This is the policy the robot's going to consider running, okay? Then what we're going to do is for every other reward function we sampled during MCMC, Ri, we're also going to solve for the optimal policy for that. Really intractable, I know. We'll get back to that. Okay, so now what we have to do is we have to think about what if our map wasn't really the true reward function in the person's head, right? What if some other reward function Ri was actually the true reward function? How badly are we going to do when we run our map? So now we have to calculate a bunch of policy losses, right? So for every Ri that could have been true, we have to say, well, what's going to be the value of running our policy, pi star map, if Ri is actually true versus running the policy that's actually optimal under reward function Ri, right? So that tells us how badly we're going to do compared to optimal for each of these reward functions that could have been true. So now this is going to give us a whole distribution of policy losses. So then we can basically sort those, compute the alpha value at risk, put a single-sided confidence bound on it. And now we're at that point where the robot can either say with high confidence, I think I'm almost as good as you at this task, or I can't tell you that and I need more data. So you could do a couple things at this point. The robot could either just say, hey, give me more demonstrations, which not all that informative, might be difficult, or you can do something active. I'm not going to have much time to talk about this today, but we have a couple different papers on this that use either an information theoretic or a risk-based criteria that tries to push the risk down directly in order to ask certain types of active queries that can help us zero in on what we really think the reward function is. And then we just loop. And you can loop as long as you need to until you either get sick of teaching the robot or you get the kinds of guarantees you want. So I'm just going to pause there very briefly because this is kind of the framework that's going to sort of frame the rest of the discussion. So any just quick clarifying questions on the framework itself?
I have one question.
Yeah, Dave.
So here you chose our map and then PyStar map, but the what you're trying to optimize is the value at risk, right? So is PyStar map necessarily the best choice for that objective?
No, I wish I could get into this more. So we have a new paper that just got very good reviews at NeurIPS. I think it's going to get in, but that actually just does policy search by trying to minimize the conditional value or maximize, sorry, the conditional value at risk directly via a sort of convex approximation to CVAR. So you're right. This is more just kind of for understanding an example. And here we're not actually optimizing in this pipeline I just showed for the value at risk. We're just picking a fixed policy, PyStar map, and we're seeing what the value at risk of it is and making sure it's not too risky. But you're right that what we really want to do at the end of the day is optimize for the value at risk, which, yeah, we have a paper now that does it, but I'm not going to talk about it today.
Got it. Thanks.
Anything else briefly?
I have a clarification question.
Sure.
Are you weighting this loss by how probable that reward function is under your likelihood?
No, because MCMC kind of just does that for you anyway, right? You're getting samples in the right amounts, depending on how likely the samples are and the rejection probabilities. So you don't have to weight any of the samples.
All right, gotcha. Thanks.
Okay, I'm going to move on then. So, just briefly, I do have a couple slides about the active learning component. So yeah, instead of just randomly asking somebody for more demonstrations, they don't really know like where the robot's knowledge gaps are. So we do have a couple papers on addressing this. So just a quick example, maybe the robot's supposed to go put something over on the shelf, right? And so it just shows a trajectory to the person, maybe via graphic interface like this, and says, hey, what do you think about this trajectory? And what we ask them to do is just segment the trajectory into the parts that are roughly optimal and roughly suboptimal. And they say, hey, these green parts are fine. I don't like the part where you wandered in front of the TV. And then we can use that to update our belief over reward functions. Now, the trick is, how do you actually generate these trajectories in order to have high information gain in expectation, or in order to push down the risk as much as possible in expectation? And so we have a couple papers looking at that, trying to do it from both perspectives. Okay, but stepping back for a moment, forget active learning, just our standard pipeline. Let's just take a look at some numbers at how this performs compared to the worst case analysis that we started out with looking at. Okay, so we don't want to get too caught up in numbers here, but there's really just two numbers that are important here. So if we compare our bound, top line, a 95% value at risk bound, to the same type of bound in the worst case, what we see is that with a single demonstration, we can get the same tightness of bound, whereas the worst case method can get with 23,146 demonstrations. So this is a 4 order of magnitude improvement, and we're not violating, in other words, our bound isn't wrong more than we say it's going to. You know, this is 98% accuracy. We claim it's going to be 95% accurate. So this is a huge gain. Again, our algorithm's intractable, but if you can pull this off, you know, this is a huge efficiency gain in terms of the amount of demonstrations we used. So if we can make this efficient, this will be very, very exciting. To give you a more qualitative view of what's going on, though, I'm going to claim that not only is it more efficient, but it actually, non-worst case reasoning allows for sort of qualitatively better risk reasoning. So here we have a demonstration. It avoids cars. It has the agent's the blue car, and it has no lane preference. It just flits around randomly, but makes sure it avoids cars. And the task is to take these 3 policies down here and rate them in terms of riskiness. Okay, so, oh, sorry, one of the videos isn't playing. But this is the safest policy. It avoids cars, but it prefers the right lane. This stays on the road, but just randomly moves around and ignores other cars, so it sometimes hits them, but it has no lane preference, much like this one. And this one is actually nasty and seeks out collisions, okay? So left is safest, right is riskiest. So what happens if we ask the worst case algorithm to rank these in order? It gets the ranking almost completely wrong. In fact, it thinks the safest policy is the most dangerous. Why? Well, in the worst case, it is. Why? Well, remember how we were talking about how these things try to do like feature matching, right? And they penalize the feature that's most different. Well, what's different between these? In here, we're always staying in the right lane whenever we can, except for avoiding cars. Here, we're in all kinds of lanes. And so this says, well, what if it's really important actually to be in the left and center lanes? That could be really bad, right? Whereas we get the ranking right because we say, well, look at the demonstration. There was plenty of opportunity to spend more time in the left and center lanes where we weren't forced to be in the right lane, but we were there anyway. So that wouldn't make sense if the left and center lanes actually mattered. So, so we're able to reason about this whole distribution of reward functions that could be true. And sure, there is a small probability that it matters to be in these lanes, but overall it doesn't contribute a lot to the total probabilistic risk profile. So we're actually able to reason more coherently about risk as well. Okay, so that's all great news, but like I said, it's intractable. So there are two major problems we need to fix. Because in what I just showed you, there's this like MDP solver buried inside it where we need either a model or all this inference time data. We need to get rid of that. And we also have to evaluate all those policy losses, which means we have to do policy evaluations. We need to be able to do that accurately and efficiently. So parts 2 and 3 of the talk are going to focus on those aspects and making them efficient. Okay, so I've got a beef with inverse reinforcement learning. There are two big problems with virtually all the algorithms out there. One is this problem that I've already kind of mentioned, which is that there's policy learning in the inner loop. You either need a model or a lot of inference time data. Because some methods, like the ones we were looking at, like the original Abel-Ing version, learn an optimal policy or value function for every candidate reward you're kind of checking. Or others like Gale or the other like adversarial algorithms kind of go back and forth and alternate policy updates and reward function updates, but they still require a lot of inference time data. This is a problem especially for like something data poor like robots. There's an even more pernicious like philosophical problem though I have with inverse reinforcement learning, which actually I mentioned to a few of you during my conversations today, which is that it can't outperform the demonstrator. Or at least not significantly. We like to tell this story about IRL that says, oh, it's inferring the preferences or like the intent of the demonstrator. But I think that's just patently false, because if it was, it wouldn't over-imitate and mimic their mistakes. It would do what their intent was. Even like 6-month-olds are good at this. You show them something and you accidentally drop it or make a mistake. They don't imitate the mistake. They understand what the intent was. Our algorithms don't. Why not? Well, because they match feature counts, or they maximize a likelihood function or something. They're trying to match exactly what you're doing when they're working their best. And this is because they're making the assumption that the demonstrator is optimal or near optimal. And I think that's a terrible assumption, and it will always prevent us from outperforming the demonstrator. Now, here's the interesting thing. At first glance, it doesn't seem like these two problems are connected in any way. And it turns out they're deeply connected. And so what I want to challenge is this assumption that IRL should assume the expert is near optimal. And it turns out by challenging this assumption, we're going to fix both of these problems at the same time. And so I'm going to argue instead that if we have demonstrations that might be even highly suboptimal, if we have a ranking over them telling us which ones are better than the others, it's going to fix both these problems. We won't need the MDP solver or any inference time data collection, and we can outperform the demonstrator. All right, so how's that work? So we have this algorithm that was at ICML last year called TREX, which stands for Trajectory Ranked Reward Extrapolation. Forgive the silliness. But the way it works is at a very high level. Imagine you have some demonstrations for a game like Pac-Man. And I give you some ranked demonstrations that I say, this one's better than this one. And as they get better and better, Pac-Man eats more food and gets eaten by ghosts less often, right? And so how would we do better than the demonstrator if they weren't very good? Well, one thing we could do is we could look for trends, right? We can look and say, oh, well, as the demonstrations get better, typically Pac-Man eats more food and avoids ghosts more. So let's just try to use RL now to learn a policy that maximally eats as much food as possible and avoids ghosts as much as possible, right? Easy. Now, you can imagine where that would fail. Let's say I show you some suboptimal demonstrations of eating in real life, and I eat a little bit, and I eat a little more, and I eat a little more, and I say, hey, better, better, better. You might assume that just eating as much food as possible is good, right? And make yourself sick. So the way what you would need to get that right is you'd need to see far enough along the curve that if you ate enough at some point, utility starts to go down. As long as you saw those demonstrations, you could learn the right features so that you kind of learned the right way to extrapolate. So we are assuming that you've kind of seen enough of what this fitness curve looks like to be able to extrapolate properly. But the idea is to look for these trends so that we can go beyond. And so that's where the extrapolation bit's going to come from. But the thing that's going to make this so computationally efficient is it turns out that this view of things is going to allow us to turn the reward inference problem from like this complicated MDP solver inverse reinforcement learning thing into a much simpler, just pairwise classification problem, right? And so we're just going to take any two demonstrations, and whichever one is ranked higher, we're going to say we want to search for a reward function that gives more total return to that trajectory than the one that's ranked lower. That's pretty much it. We just use this exponentiated pairwise loss to enforce that, and it just becomes a classification problem. So now it's fully supervised. There's no policy learning. There's no inference time data collection. It's just more like a human does it. You look at something, someone behaving, you don't simulate a bunch of crap in your head or anything. You just know what they mean, right? You just do it. It's also a learning from observation algorithm. We only need states. We actually don't need the action labels, which is pretty cool. We have extrapolation potential, like I mentioned. And it turns out that it's pretty much the only reward inference algorithm we know of. And we compared to a reasonable number of them that works reliably on high dimensional tasks like Atari. And in fact, with some clever data augmentation so that we don't massively overfit, we can do this with about 10 demonstrations with no pre-training whatsoever. So this is actually pretty surprising. I'll get to some of the stupid things that it does in a little bit, but let's look at the good results first. So here's some ranked demonstrations for the half cheetah task in Mujoko. The numbers below represent how far it gets in a fixed amount of time. We have kind of a face walk, a faster face walk, and a semi-stable walk that sometimes falls on its face. So we give these demonstrations, we tell TREX to infer a reward function, then we use PPO on top of that to do RL. And what we find is that here's the best demonstration, and compared to that, TREX learns a nice coherent gate that gets a significantly better score than what the best demonstration got. Extending this to Atari, we see in this game Space Invaders that we're actually able to get a score that's more than double what the best demonstration is. Now, one thing that's interesting is TREX sometimes has this causal confusion problem where the better you do in a game, the longer you live, the more that these little structures you can hide behind get shot up. So sometimes it thinks that the thing that explains why the demonstrations are ranked the way they are is how destroyed these shelters are. And then it'll just learn to sit there and shoot the shelters forever. Because that's correlated with return, but not causal of it. And that's a problem. We have fixed this by, I'll introduce later, a Bayesian version of TREX that addresses this. We've also used human gaze to see what people are paying attention to when they give these demonstrations. And it turns out that gaze works really well as sort of supervised attention for what features you should be paying attention to at any moment. And it's actually very good for doing sort of causal disentangling. And we're finding something on the entire Atari suite. We just got results the other day that we're getting about 400% improvements for imitation learning just based on using gaze. But don't quote me on that. That's like a brand new result. Okay, but to convince you that this is actually doing something interesting extrapolation-wise, we asked T-Rex, what do you think like the worst possible frame is and the best possible frame? And it thinks that this frame stack with like all the aliens there is the worst, and this frame stack that is completely a screen clear is the best. And interestingly, it never saw a screen clear during training. The demonstrations were suboptimal enough that it never saw a screen clear, but it's able to realize that this is kind of, you know, what it thinks the best thing that can happen is. And so it really does appear to be extrapolating coherently. And in fact, if we plot our predicted returns based on our learned reward function with ground truth returns across a bunch of different domains, we get something. We've only seen the red points during training. Blue are kind of test points where we're testing our extrapolation capabilities. And we're seeing something that's often roughly linear, or at least linear in the features, you know, we discovered, but linear in this plot where we're plotting the returns. But even if it doesn't have to be linear, it really should just be monotonically increasing, right? And we don't see that everywhere, but we see that it is learning pretty reasonable things and seems to have strong extrapolation properties. And finally, if we just look at some numbers, what we did was compare T-Rex in green here. When it was learning from, this is the quality of the best demonstration blue, and we did it in a couple different scenarios with increasingly good demonstrations. And we compare it to two state-of-the-art imitation learning algorithms, behavioral cloning from observation and generative adversarial imitation learning, or GAIL. And we also compare to running PPO, our RL optimizer, on the ground truth reward as well. And we see that almost across the board, T-Rex does significantly better than both the best demonstration and the competing algorithms. And in a couple cases actually does almost as well as the ground truth reward, which is fairly surprising. And this extends to Atari, which has been notoriously hard to get inverse reinforcement learning to work on. And so the performance differential here is even more stark in Atari domains. Okay, so that's great. You know, we have this now state-of-the-art inverse reinforcement learning algorithm that can do super fast, accurate reward inference, extrapolate, but it's still, we're not in like a standard imitation learning setting, you might say, right? We're still assuming we have access to these rankings, which is not ideal. And so we have another version of this that was a Quora last year called DREX, which stands for disturbance-based reward extrapolation. And this is where we try to do the same thing, but in a standard imitation learning framework. So we start with just a pile of unranked demonstrations, and we first perform behavioral cloning on them and get a policy. And then what we do is we start generating rollouts from that policy. And at first we just generate normal rollouts, and then progressively we start adding more and more action-wise noise as we generate more trajectories. So the later trajectories are more noisy than the earlier ones. And as long as the demonstrator, and thus the behavioral cloning policy, was better than random, we assume that as we inject more noise, in expectation, we're going to get worse and worse performance. And so now this gives us sort of a pseudo-ranked set of demonstration trajectories that we've generated. We stick them into T-Rex, and it turns out that in most cases, this works almost as well as T-Rex with sort of ground truth labeled trajectories. So now we can do the same thing, but without requiring anything extra of the demonstrator. So finally, we want to loop this all the way back to the safe IRL stuff I started talking about, right? So far, you know, we have this nice algorithm now for IRL, but it just gives you a point estimate of the reward function. It doesn't give you a Bayesian posterior like we need for reasoning about uncertainty. So we have, this was just an ICML this year, a paper called Bayesian REX that is, as it sounds, a Bayesian version of this same idea. So here's the way it works. It works in two steps. First, we have a feature pre-training step. And what we do is basically just do T-Rex. We have our ranked demonstrations. We run T-Rex, not because we care about the reward it spits out, but because we want to learn good features to represent rewards. But we don't just want to focus on that one reward that T-Rex is going to output. So we add a bunch of auxiliary tasks as well, things like forward dynamics prediction, inverse dynamics, TD error, a whole bunch of other stuff we define. So, and we do something where, you know, they all share features, but then they each get, every auxiliary task gets its own just single linear layer after that. And the reason we do a linear layer is because we want to learn features that in linear combination with each other can do interesting things. And here's why. It's going to make something really efficient later when we go to do MCMC. After we've done this pre-training, what we do is we take all the ranked demonstrations and we shove them through this network, and we get a vector of feature counts for the entire demonstration. There's just, a single vector as big as the number of features, right? And we do this for all the demonstrations. And now, when we go to do MCMC, we just start drawing weight vectors. And when we sample a weight vector, what we want to know is how much total return does it assign to each of these ranked demonstrations? How do we find that out? Well, all we have to do now is we've pre-computed and cached this. So we just have to take the dot product between W and each of these feature count vectors. And that tells us how much return each of these gets under that reward function. So now it's super cheap to do MCMC, now that we've frozen everything. And so now we just need a likelihood of how we know to accept or reject the MCMC proposal. And again, it's just going to be this sort of pairwise loss again, that we should respect the ranking. We should be giving more return to things that are ranked higher. And so we have this exponentiated pairwise loss. And eventually, we repeat that n times, we end up with a demonstration over, or a distribution over reward functions. So now we've come full circle. We have a efficient inverse reinforcement learning algorithm that can give us this distribution over reward functions, but in an efficient way that could actually be used on high dimensional problems or a robot. So let's do something cool with it. So first, we just kind of did a sanity check to make sure we didn't break everything and that it's competitive with T-Rex. It is. Good sanity check to do. But we also now have this ability to reason about risk. And I just want to share one experiment briefly that I think is really neat. So there's this game called Beam Rider in Atari. And it has this interesting property that once it starts, or once you lose a life, I think, you have to hit a button. And if you don't hit a button, the game never goes anywhere. It just kind of sits at this screen with things moving around, but you just live forever and you get 0 score, okay? So this is an interesting domain for a reason that'll become apparent in a second. So what we wanted to do was we wanted to see what would a point estimate of a reward that would come from T-Rex or the map from the Bayesian version. What would it think about how good certain policies are compared to a risk-based analysis that uses the whole posterior? So what we did was we handcrafted 4 policies for this game, A, B, C, and D, that are increasing order of good. You can see their ground truth scores here increasing. And then we also created a no-op policy that just does nothing, okay? So think about this. As you do better in a game, you typically live longer, right? And so one way, if you trained on policies that kind of look like A, B, C, and D, for example, one way to generate a reward function that respects the ranking is just give a constant reward at every time step. And then longer trajectories that live longer will have more total return. Great. Except what breaks that? Well, look how long the no-op policy lives. It lives until the simulator times out. So if you look at the mean reward from the Bayesian REX, or what T-Rex would give you essentially, it gets A through D right. It thinks the no-op policy is actually best just because it lives a long time. If we look at the 5% value at risk though, it gets A through D right, but it thinks no-op is terrible. That maybe it's not bad, but that at very least it's very risky, right? And so it allows us to cull that and realize that is risky, which I think is just a really neat result that we're able to kind of make inferences like that, and in a very fast, efficient way with a very small number of demonstrations that we're learning from. I think it was 10 again in this case. Okay, so we're almost done. Let's see, I'm a little short on time. Okay, so I'll breeze through this last section. But we've talked about this framework for safe imitation learning, how to make it efficient by getting that MDP solver out of the inner loop. But now we still have to do these policy evaluations at the end to actually gauge this distribution of policy losses. So how can we do that efficiently? And I think this work is hopefully of interest to a pretty broad community of people, because efficient policy evaluation is sort of everywhere. So just as a reminder, the safe OPE problem is just determining a lower bound, probabilistic, on the expected performance of one policy given data generated by a different policy. So if we weren't doing this off policy, if we were just getting on policy data, we would just Monte Carlo it, right? Roll out the evaluation policy a bunch of times, average them, boom, done. If we're doing off policy, we need to correct. So, a common way of doing that's importance sampling. You just correct the returns by the probability of that trajectory under the evaluation policy divided by its probability under the behavior policy. And we call that the IS, or importance sampling estimator. This is still not safe. It doesn't give you a confidence. So if you want a confidence, you have to do the standard thing, use a concentration inequality, throw like a Hufting style bound or something a little bit smarter on it. And that gives you a lower bound that says, hey, your policy is no worse than some constant with probability 1 minus delta. So there's a lot of good work on this. My colleague Phil Thomas, that I do a lot of work with, works a lot in this area. But this stuff is like typically really, really sample efficient. Like we're talking millions and millions of samples for reasonably simple problems. So this isn't something that can be used in robotics. So what can we do to make policy evaluation better? So we've done a lot of work in this area. I don't have time to talk about all of it. So I'm just going to touch briefly on 2 recent results that I think are cool. So one of them is we wanted to challenge the assumption that there's kind of this assumption in policy evaluation community that if you have a policy you want to evaluate and you have a choice, you haven't done anything or collected any data yet, and you can either just do the on-policy thing and Monte Carlo it, or you could collect some other data from some other policy and like importance sample, you should always just do the on-policy. And in fact, if you look at in the Sutton and Bardo 2nd edition of the RL book that came out pretty recently, they actually make a specific statement in there where they say, on-policy evaluation is inherently lower variance than off-policy evaluation. And this is simply not true. This is actually very, very not true. And in fact, if you see Rich Sutton, badger him about this, because I have been trying to get him to change the book now for over a year, and he is stubborn. So help me on my quest. But we've shown that it can be much more efficient to use off-policy data. And just to give you a brief insight into why that is, let's take a look at this really simple sort of bandit style example. So you got one state, you have your evaluation policy. 1/5 of the time it takes action A, you get plus 50. 4/5 of the time you take action B, it gets plus 5. We take the expectation of this policy, it's 14, okay? So we could Monte Carlo this, right? Get a bunch of samples of taking A, taking B, and eventually we will get, an average of 14, right? Let's think about another thing we could do though. We could take something, I'm not just going to call it a behavior policy, I'm going to call an optimal behavior policy. And it turns out for a pretty wide variety of problems, an optimal behavior policy does exist. But even for the rest of problems, there are much better behavior policies typically than just running the evaluation policy in Monte Carlo again. So instead, we're going to run this behavior policy in importance sample. And here is a policy that I claim is, quote, optimal. And here's what I mean. A, 10/14, B, 4/14. Why those numbers? Well, let's say we're just going to take one sample, just one, from this and try to come up with an estimator of how good pi e is. Well, if we importance sample and we took A, we get 1/5 over 10/14 times 50, which is 14. If we took B, we get 4/5 over 4/14 times 5, which, hey, it's also 14. So with one sample, no matter which action we took, or in the more general case, no matter which trajectory we get, we always get exactly the right answer every time with one sample. So we have a zero bias, zero variance estimator with a single trajectory. We're done. We just needed one sample, right? So that's why it's the optimal behavior policy. It's kind of amazing that this exists. Statisticians know this and would say like, yeah, of course, but this kind of isn't well known, I think, in the policy evaluation literature. So the problem is that we don't know what this policy is. So what our suggestion instead is start with the evaluation policy. And after you roll it out once, do an update to your behavior policy and keep updating toward policies that are going to lower the expected mean squared error of your importance sampling estimator. And you can do this via something that looks like the policy gradient theorem. So we derived something we call the behavior policy gradient theorem that actually is the derivative. We compute the gradient of the mean squared error of our importance sampling estimator directly, so that we can walk toward behavior policies that are going to sample more intelligently and eventually walk toward, hopefully, the optimal behavior policy. And this gets really great results where we often get like an order of magnitude reduction in variance of our estimator within about 10 samples. Almost out of time, but very briefly, I just want to highlight one other result, which is that we challenge a really common sense seeming assumption that if the behavior policy is known, if you know like the probabilities with which actions were taken, you should just use them directly in importance sampling instead of like, I don't know, estimating them with regression, for example. There are times when you might need to do that, like a doctor gave you the result, the decisions, and you don't know what the probabilistic policy in their head is, but otherwise you usually have access to these numbers. And it just seems common sense to use them. But we showed that it's often, very often, better to use an empirical estimate of behavior policy rather than the known behavior policy, because it actually corrects for sampling bias in a really interesting way and reduces the variance of your estimator most of the time. And in fact, even if the policy you ran to gather the data was Markovian, it's often better to do a non-Markovian regression, and it corrects for an even more subtle form of sampling bias. So anyway, take a look at the paper if you want to know more details. It's just a neat little result. Okay, so I'm going to wrap up. Let's put this all together. I want to do this on a robot. And in fact, we were starting to do this on a robot before COVID hit, and then it ruined everything. So I'm sorry that this is a Robotics Institute talk and I'm not showing you more cool robots. I do have one video at the end I'll show. But you know, we have this safe imitation learning pipeline. We've made it efficient with both efficient IRL and efficient policy evaluation. We want to do visual manipulation now. And so we actually had this like air hockey table we built, or that we bought, and we retrofitted it so that it's like tilted toward the robot and the puck always comes back, and you can play this like kind of like virtual game of Breakout on it. And anyway, I think it's a cool domain. It's coming, hopefully, eventually, now that we have access to the lab again, but we're not quite there yet. But theoretically, I see no reason why this should not scale up, given that it works in Atari. We've actually done it, some early stuff in simulation as well, that seems to be looking good. But I just want to emphasize that everything I've talked about today is like statsy. We're looking for like little statistical tricks to make things better. And my feeling is that we can only get so far by doing that. And at some point we have to start looking at other sources of data. And so I have a whole other body of work where we've been looking at using other modalities of data to reduce our uncertainty about what people's intentions are whenever they show us demonstrations. So can we draw on auxiliary videos of similar tasks that aren't quite the same, but that maybe share some pieces of subtasks? Can we leverage natural language instructions or narration of demonstrations to better understand what people mean and reduce our uncertainty over that distribution of reward functions? We've done a lot of work with gaze, as I mentioned earlier, as a form of supervised attention to help guide us toward features that are really important for understanding and generalizing the demonstrations. So I think this is a really important line of work in addition to the statistical reasoning too. We've also been looking at theory of mind. So thinking about what if we consider that humans aren't necessarily optimal in the way they behave, but maybe they are like near information optimal. So like, for example, someone, if you give them a budget of 2 demonstrations, is probably not going to show you the same thing twice in a row, because that's not informative. And if something's important to them, like avoiding the laptop with a hot drink, they're probably going to show you that. And so if you just make this little extra assumption that they're not just behaving optimally from a starting state, but maybe actually picking a starting state in order to show you something informative, how much more can you infer about their preferences? And it turns out the answer is a lot, just by having this mental model of them. And so we have a paper that's sort of based in machine teaching theory that goes into this. And finally, you know, I've been talking, hey, it's a robot. I've been talking today about reinforcement learning and doing that on top of the reward function. But there's no reason you have to do RL. you can do planning too. And in fact, we have a line of work building really efficient hierarchical POM-DP planners that can reason about uncertainty, make sure with high certainty we get to some particular configuration of the world, and can even learn about from demonstrations like how an articulated object like a stapler works, reason about that all together, and perform tasks with high confidence. So I'm not just interested in RL, and if you're interested in planning, you should also think about, you know, how to get these objectives and preferences out of people and elicit these rather than just writing them down. And so with that, I'll close. These are my students who obviously did all the really hard work. So thank you to all of them. And yeah, thank you to all of you for being here. And I'm happy to take any questions you have.
All right, thank you very much, Scott. That was excellent. I think we have one question to begin with in the chat from Zucian. Zucian, do you want to ask your question?
Yes. Could you go back to the slide for the off policy evaluation with importance sampling, the on policy evaluation with importance sampling? The example, yeah, because is that a coincidence here? Because you chose the probability for the pi b star.
Yeah, we did. So this is an existence proof. It is not saying how to find that policy. So it turns out under a certain set of assumptions like deterministic dynamics and a couple other minor assumptions, I think all positive reward in optimal behavior policy always exists, provably. When you have stochasticity, it might exist, but it doesn't necessarily. But we've never found a case where there aren't significantly better behavior policies than just running pi e all the time.
Okay, I see. Is there any analysis about which one would be more efficient in which cases?
So, I mean, it's shocking how bad running pi e really is. There are tons of choices that are better. And if you follow that gradient, you know, that we have here, in expectation, you know, you are likely to end up with something that is going to be lower variance even within a single step. And in fact, you could actually, there's probably concentration-based ways that you could gather enough samples until you were sufficiently confident in your gradient step that you were actually going to be lower variance once you took the step.
Thanks.
Harshit?
Hi, so my question is like, how do you decide the extrapolation amount in T-REX? Like, doesn't it depend on the environment?
Well, it basically tries to extrapolate infinitely because it just says like, it just finds a reward function that it thinks respects the preferences, right? Gives higher return to the things that are better. And then it just tries to maximize whatever that reward function is, right? So it kind of shoots for the stars. So, you know, if we look at, let me find the plot that I'm thinking of. So if we like look at like this, you know, we kind of see these down here, these suboptimal demonstrations. And if we plot predicted performance from our algorithm versus true performance under the ground truth, you know, we're trying to find a reward function that, you know, makes them look, you know, roughly linear, or those points should at least be monotonically increasing. And then we just try to like maximize that reward function. So we're pushing it all the way. So we are definitely hoping that it's still valid out here. And like I said, that can break because if you only see demonstrations of people eating more and more, you're going to think eating infinitely is the best thing you can do. The only way that you would extrapolate correctly is if you saw at least a couple demonstrations where eating more was worse than eating less. And then you can extrapolate correctly and kind of guess as to where that sweet spot is. And you'll find a reward function that orders things in the right way with some like nonlinear features. But yeah, you have to have seen good enough demonstrations such that the trend is going to be legit.
Just a quick follow-up. So like when you're training on only the expert trajectories, like how do you ensure that the reward at all other state space is kind of less? If like there's overestimation due to like lack of data, when the policy is trained using PP on that, it will like go there.
So I'm not sure I understand the question. So are you asking just how do we not overfit when we're fitting a reward function, or is it something else?
So the reward function, like where there's no data, suppose for some state action pair that is not in the distribution of expert, our neural network might like predict like 10,000 say reward there, and your PPO will just go there. So how can we fix that?
Yeah, that's a good question. I mean, I think that's where the Bayesian, well, so that's one reason why we use data augmentation methods, and that helps a little bit, but not really. I think the real answer there is that's where the Bayesian framework comes in. That, like, you know, the Bayesian framework considers all possible reward functions essentially, and what their probability is given the demonstrations. And so if there are multiple explanations, one where there would be 10,000 reward in that state and one where there would be negative, 12 or something, it's going to have to consider both those possibilities. It's going to have to weight them by their likelihood. And we're going to have to use, we shouldn't pick a map reward or something, or a mean reward. We should really pick, we should do a risk sensitive analysis. And we should make sure that we're really picking parameters for how much risk appetite we really have. And if we pick that right, we'll make sure that if something really is risky, that we don't do it.
Okay, thanks. Yeah.
Chris, can I ask your question?
Yeah, so thanks, Scott, for the good talk. A lot of stuff to think about. So I guess I was thinking very broadly about kind of the target of wanting to have, I think, policies that are safe or have some kind of guarantee of safety. And one of the things I kind of noticed as I was listening to the talk is that sometimes the whole training process to get to that point involves non-safe like algorithms. So things like, adding random noise to actions, or I guess in simulation you could do this, but evaluating your policy and things like that many times, that might be dangerous or not possible. So I was wondering if there are like maybe some other options. Is there a way to like ensure some kind of safety during training? Because some real world problems have this kind of flavor to it. Like you can't really go crazy with the simulation.
Yeah, absolutely. So so let's ignore the REX thing for a minute, where we were doing noise modified rollouts. Let's say we have access to the rankings. So we have the demonstrations, we have the rankings, REX is fully supervised, nothing unsafe happens there. The only opportunity for unsafe then is when we run RL on top of it. And there are these safe policy improvement algorithms. I think the best one I know of is this one called Daedalus that was developed by Phil Thomas and Emma Brunskill, actually when they were both at CMU. We've been building some stuff in this regard too that we're working on, where basically you just want to set a confidence level, and you want to make sure that every time you take a learning step, that it is monotonically improving by at least epsilon over the previous one. And even the exploratory actions you're taking are not exploratory, because you're just doing rollouts of your current policy you trust, and then you're doing off-policy evaluation. So that means it's kind of slow. You can't take like large steps, because as soon as that KL divergence between your old policy and your new policy gets too big, the importance weights all blow up, everything just kind of goes to hell. But yeah, you can do this. So, I think it needs a little more work, but actually you're giving me a chance to plug something, a sort of big idea I'm trying to get out into like the academic consciousness, which is that everyone sees safe learning right now as this like niche little area that's like cute, for people who care about safety, but like no one else should care about it. And I think that for two reasons, everybody should care about safe learning. One is that eventually, as we get more things out in the world, like they just need to be safe. Like not even because they're necessarily dangerous, but just because they need to work or no one's going to want to use them. But the second reason I think is even more interesting, which is I am convinced that safe learning algorithms don't have to be slow. And in fact, they are eventually, in maybe another 5-10 years, going to dominate unsafe learning algorithms in terms of computational speed. And the reason is that often when you're considering safety and the possibilities of what's out there, you're pruning a lot of your space. You're not doing stupid things. You're not taking bad learning steps that aren't monotonically increasing and crashing your performance. You don't have to run RL 50 times with different hyperparameters and see which ones actually happen to work. You can tune them on the fly. You have all these opportunities. And so I really see safe learning, like I want to see it pushed as the dominant learning paradigm. So sorry to use you as a soapbox, but that was,
Thanks.
yeah, I hope that answered your question too.
So we have time, I think, for one more question. Dave?
Okay, I just have a really small question. So you've talked about like Bayesian IRL and things like that. So how important is the prior and how do you pick it?
I mean, so, okay, I'll say two things. One of the things I'm going to say is that it doesn't matter really. We just use a uniform prior and everything kind of works out hunky-dory. But obviously, as you know, like uniform is not like uninformative and it, brings its whole own set of baggage with it. And I think it's something we need to think a lot more deeply about. It's really hard to know, like, what is a prior over human behavior and things that people like to do. And yet, I would love to do a large scale study on this and figure out, like, what's the type of stuff humans like to do? Because, like, I should not be having a uniform prior on, like, well, maybe somebody is trying to, like, place this cup here, and maybe somebody is, like, trying to act all wiggly and place it so that it's, like, in line with, like, Saturn or something, right? Like, I mean, I'm sure there are people that do that, but it's not common. And so I would love to, like, get this data set that told us something about, like, a prior over human stuff that people do. But I don't know exactly what the right experimental system is to get that out of people.
Cool, thanks, yeah.
Okay, so we're a little bit over time already, so I suggest we stop there. There is the link for the Gather Town is in the chat, and I'd like everyone to join me in thanking Scott again for the talk. It was really great.
Thanks so much, everyone. This was fun. And I'll see you all over in Gather Town.